This is problem number 7 from section 5.4. In this problem it says there is a relation between an airplane's weight, x, and the runway length, L, required for takeoff. So right away I'm going to kind of write this out. This is x stands for the weight, and L stands for the length. So we're going to say, after this, let's finish reading. So I wanted to write those two things down right away because they tell you it right away in the first sentence. All right, so there is a relation between an airplane's weight x and the runway length L required for takeoff. For some airplanes, the minimum runway length L in thousands of feet may be modeled by this logarithm, where x is measured in thousands of pounds. Part A. They want you to evaluate L of 1,000 and interpret the result. So we're going to have L, that's of 100, not 1,000. So L of 100 equals 4.5 log of 100. So 4.5 log of 100 log 100 is 9. So what does that mean? That means with a runway length of, with a plane weight, so x is the weight, so, and the weight is in, what do they tell you? Where x is measured in thousands of pounds? Okay. A 100,000 pound plane needs, now this is measured, this is the L of x, right? So that's the length, but in thousands, it needs 9,000 feet for takeoff. Okay, that's what the interpretation of that is, because this is 100, and I should actually put that in there. This is weight in thousands, and this is length in thousands. It makes it a little easier to see. So 100,000, so a 100,000 pound plane needs 9,000 feet for takeoff. Okay, makes sense. Part B, heavy plane, lots of runway. If the weight of an airplane increases tenfold from 10,000 to 100,000 pounds, does the length of the required runway also increase by a factor of 10? Explain. So, I don't believe it does, because we have a logarithm here, and if you know what a logarithm does, a logarithm with an input will spit out an exponent. And when it spits out an exponent, that exponent is only going to have an increase in factor from 10,000 to 100,000, because this is log base 10. It's going to increase by 1, essentially. Let's take a look, and let's just compare them. So let's go 4.5. So we're going to plug in, well, L of 10,000, and we're also going to plug in L of 100,000. If I plug in L of 10,000, I get 4.5 log of 10,000, and then this one would be 4.5 log of 100,000. All right, now I'm going to plug in actually what the log is. So log of 10,000 is 4. And log of 100,000 is 5. So for this here, this is 4.5 times 4, and this is 4.5 times 5. So this increased by 10 times. I move 10,000 times 10 is 100,000, but this part did not increase by 10. And you can see that there when you plug in 10,000 into a logarithm and then 100,000 into the logarithm. Base 10, it's just giving you the exponents. Like 10 to the 4th is 10,000. 10 to the 5th is 100,000. So it's not increasing at the same rate there. Now this would give you what, 4.5 times 4 is 18, and 4.5 times 5 is 22.5. So the difference between these two is, remember this is in thousands of feet. So this is 18,000. We'll go ahead and write that out. So L of 10,000 is 18,000, right? And then L of 100,000 is, add 1,000 there, it's 22,500. So the difference between them is 4,500. So what we would say there, does the length of the required roadway also increase by a factor of 10? And the answer to that is absolutely not. It only increases by 4,500 feet. So no, the increase is less than a factor of 1. Or I would say less than a factor of 2, because it's not even double, right? The increase is only 4,500. Now part C, generalize your answer from part B. So if we're generalizing that, for every increase of a factor of 10, we're technically only increasing by a factor on this side of 1. All right, so we could say for an increase of 10, maybe we'll say for an increase of 10, maybe we better use the 4,500 amount. We are only increasing 4,500 feet. And that's the solution.